Hello everyone. So here we have a inverted pendulum on the card, which we'd like to control. Let's draw it like that. So our inverted pendulum is this one, and by moving or applying some force on this card, we'd like to balance it on the vertical position. This is the idea. Of course, it has some other states. This one is theta, and then it has omega or theta dot, which is angular speed. Then it has a position of this card and derivative of this position, which is velocity. So here is our model in Simulink, and this block represents pendulum and card math model. Why math model? Because it doesn't have any resistance from the air or damping from the air or from the mechanical damping, and we applying, so the disturbance is like that. It's just a pulse at second one. So let's try running it. So here is our animation, and of course, because there is no damping, it just rotates infinitely. Good. Now, what would happen if we use only one state, theta, and we'll try to control our inverted pendulum by using only theta. And here on the left side we have membership functions of theta, which is input, and it works from -pi to pi, and we have output, which represents the force we apply, and the rule is made so that when we have negative theta, we're applying negative force, and when we have positive theta, we applying positive force. Okay, let's try to run this model now. So as you can see, controller, fuzzy logic controller tries to do its work, but it's not enough, because slowly carrot is moving, and carrot is trying to stabilize the position of pendulum, and it's moving. Here I have added one more state, which is theta dot, or derivative of theta of the pendulum. So I added membership function, and it's from -5 to 5 in this range. and I added output when, and or rules as well. So when theta dot is positive, it uses this purple curve, positive L, and when it's negative, it uses negative L. So let's run our model now. So here it looks more stabilized, but there are some vibrations here. The inverted pendulum is vibrating, and the carrot tries to stabilize it, and it moves to the left, which means that 2 states are not enough to make it stable. Okay, here we are using all 4 states: theta, theta dot, position, x, and x dot, which is velocity. And we providing position as a error, a difference between the current position and reference. The reference is the place where we want to see our caret. And here, so I added 2 more membership functions, which is cart position from -2 to 2, and the cart velocity, and I have added 1 more output function, ns and ps. And here it works when we have and I have added 4 more rules. And when cart position is negative, it uses positive ps, and when cart position is positive, it uses ns, negative function. And why is that? It's so because if we'd like to move to the desirable position this cart, first, so ignore this one. First we apply force to this position from this side to make move the pendulum to the opposite position to this side, and then our other functions work to stabilize it. So if we'd like to, in this case, to move our caret here, for instance, first we apply force from this side. This one moves here to the right, and then another force applies to stabilize it. Okay, let's try to run our model. So as you can see, time is running and pendulum is stable. And if we'd like to move it, so as I told before, the pendulum moves from here, and then caret stabilizes by moving to the right side. to the disabled position. This is how it works. Okay, it reached the disabled point. Now let's try it in the opposite direction. Okay, it reached the disabled position. Everything works well. Thank you, and you can download this model with all like file functions in the description.